In this lesson, we'll go over the first derivative test for local extreme values. Recall that the maximum and minimum values of a function f that occur at interior points of its domain occur at points where the derivative is either equal to 0 or is undefined. These points are called the critical points of the function f. What we'd like to be able to do now is use the sign of the derivative to classify these critical points. So our first step in this test is that if our derivative f prime changes from positive to negative at a particular point, so if our function goes from increasing to decreasing at a particular point, then we have a local maximum value at that point. So the key idea here is that we know if our derivative is positive, then our function is increasing, and if our derivative is negative, then our function is decreasing. So if our function goes from increasing to decreasing, then we have a local maximum value at a given point. Similarly, if our derivative changes from negative, so negative derivative would mean our function is decreasing, to positive, meaning our function is increasing, so our function goes from decreasing to increasing, then we have a local minimum value at our point. And finally, if f prime does not change sign, so if we stay increasing, that might look something like this, or if we stay decreasing, that might look something like this, then we actually don't have an extreme value. So we don't have a max or a min at our given point C. So if our derivative changes sign, positive to negative, then we go from increasing to decreasing, so we have a max. If our derivative goes from negative, so decreasing, to positive, increasing, then we have a min. And if our derivative doesn't actually change sign at our critical point, then we actually don't have a max or a min value. So let's take a look at a problem involving finding maxes and mins. And this is one that we've looked at before, so we'll go through the calculations fairly quickly here. So the first thing we did was find the intervals where this function is increasing and decreasing. So we took our derivative and got 3x squared minus 12, and then we wanted to set that equal to 0. That gave us x squared is equal to 4, so x is equal to plus or minus 2. And so we then set up our sign chart. Again, this is one of the previous examples that we had done. So we set up our sign chart and we found values of the sign of f to figure out what that tells us about the sign of f prime to figure out what that tells us about the behavior of f. We plugged in a number less than -2, for example, -4, and we got that f prime was positive here. So your f is increasing. In between -2 and 2, if we plug in 0, we see that f prime is negative. So we're decreasing, and then bigger than 2, f prime is positive, so we're increasing. So what we see is that at x equals -2, f prime changes from positive to negative. And this tells us our function goes from increasing to decreasing. So this tells us that x equals -2 is a local maximum value of our function. And the point here, so when x is -2, y is equal to -2 cubed minus 12 times -2 minus 5. We plug x equals -2 into our function, and we get -2 comma 11. So -2, 11 is a local max of our function. And now similarly, we see that at x equals 2, f prime changes from negative to positive. So here, our function changes from decreasing to increasing. So we see that x equals 2 corresponds to a local minimum, and our point, so if we just plug in x equals 2, we get 2 cubed minus 12 times 2 minus 5, which gives us negative 21. So 2, negative 21 is a local minimum value of this function. So let's put all of this information together to sketch a graph of our function f of x. So the first thing I'm going to recall here, just write down our function again. So it was f of x is equal to x cubed minus 12x minus 5. And we found so far the key information. We know that f is increasing on the intervals minus infinity to minus 2 and to infinity. This function is decreasing on the interval minus 2 to 2. We know that the point negative 2, 11, where our function changes from increasing to decreasing, is a local max. And we also know, max, that the point 2 comma negative 21 at x equals 2, we change from decreasing to increasing, so 2 negative 21 was a local min. So we can now put all of this information together to sketch a graph of this function. And just so that we have a point to work with, I'll say when x is 0, so we know that f of 0 is negative 5 just by plugging x equals 0 in. So we know for sure that we go through the point 0, negative 5. Now we know that our function is increasing all the way from x is minus infinity, so for all values x less than negative 2, up to negative 2. And at negative 2, 11, so let's go over negative 2. So here's our point, say negative 2, 11. So our function is increasing up until this point. So we get to negative 2, 11, and then this is a local max. And then our function starts heading back down all the way until it gets to 2, negative 21. And at 2, negative 21, we have a local min. And we said we know we go through 0, negative 5, so we come down to 2, negative 21, and then we turn around again and we start increasing, so we just go back up. So we've sketched a graph of our function. Of course, it's not perfect from the drawing on the screen, but the idea is that we use these intervals where we're increasing, so going up from minus infinity to minus 2, and then 2 to infinity, decreasing in between minus 2 and 2, and we have these local max and min values, which allowed us to actually find what these points, these local extreme values are. So the key to solving one of these problems is to use the sign of the derivative to find where we're increasing and decreasing. And if f prime changes from positive to negative, then we've gone from increasing to decreasing, so we have a max. If we go from negative to positive, then we have a min. So putting all of this together, we summarized all of the information that we learned about our graph from the first derivative, and then we're able to sketch a graph of this function.